Okay, so we have another old exam question here we're going to take a look at. And here we go. This is from 2019 fall. That's 1920 fall in my collection, exam 3. And we are going to be looking at question 2. Here it is. So this is a question about Jordan bases and rearrangements and stuff like that. The way this question is phrased is, at least the given information is, we start off with free arithmetic, right? So questions like this save you the trouble of having to do a bunch of tedious arithmetic and focuses on making the appropriate interpretations. Okay, so given that free arithmetic, a question asks, this matrix A, find a Jordan basis for it, namely the basis by which the linear transformation goes into Jordan form. So how do we get our hands on these? And isn't it just it's the columns of the conjugating matrix, right? And a lot of students will just instantly pick out and say, okay, well, there you go, boom, those are the columns of the matrix. But you always have to worry about the order. You've heard me say this a million times, and this is just yet another example. This matrix is the SS matrix. This one here is the VV, right? That's the whole idea of a Jordan form, is we're taking a matrix that previously we were interpreting with respect to the standard basis and ask, hey, if I interpret it with respect to a different basis, can I make it look like that? Well, if that's SS and this is VV, then unavoidably, this one is S to V. And this one is V to S, right? Again, that's how the Legos fit together. So putting the equation, the given arithmetic, writing it as what do these say about what's going on with respect to what bases, we see that it's actually this matrix whose columns are the basis that we're looking for, right? Written in the language of the standard basis. Okay, so that being noted, we label these columns here as V1, V2, V3, and V4. That is the Jordan basis. Okay, so again, the big foot in the door. Think about everything in terms of what bases are playing what roles with the matrices. Don't just, okay, it's always the one on the left, or if this is on the right, then that's on the left, and there's too many cases. Never get it straight. Okay, finding the eigenvectors and the eigenvalues of the matrix. Again, Jordan form's really convenient for that. In some sense, the ones that appear to be eigenvectors from the point of view of the Jordan basis are the ones that are the eigenvectors from the point of view of the Jordan basis. So we have this one unfortunate non-diagonal entry there that's kind of messing it up. And just real quick, this is an observation of the Jordan blocks looking like this, right, in our Jordan form. So those, that being the one off diagonal entry, that is the one column whose corresponding vector is not an eigenvector. So looking at the first column, only a diagonal entry. And what that tells me is that V1 is an eigenvector because there's only the diagonal entry, only a non-zero entry is only the diagonal, and 3 is the eigenvalue. And I guess I'll go ahead and tap it out here. So V1 is an eigenvector, 3 being the eigenvalue. And then likewise for the others, this says that V3 is an eigenvector, again with eigenvalue 3. And this says that V4 is an eigenvector with eigenvalue 4. So those columns interpreted with respect to this new basis, this script V basis that we just made, those columns interpreted just directly as equations are these 3 equations, thus giving us these eigenvectors. Okay. All right. Now, where things get a little bit sort of different is with part C here. And the question here is to find a change of basis matrix for which this other matrix computed by that formula is also in Jordan form. Now, the way this question is phrased is a little different from other questions on old exams and things we've talked about directly in the lecture recordings and the notes, etc. But it's touching on really the same ideas, and you just have to interpret appropriately and think about, well, what have we talked about in relation to these ideas? And it's actually going to work out pretty naturally. So first thing I want to observe is we're talking about something that is similar and also in Jordan form. Well, we have a big result about that. Similar matrices also in Jordan form. There's only one way to do similarities that are also in Jordan form, and that is just rearranging the blocks. That's the only similarity within Jordan, among Jordan forms. So we know that what we're going to be doing is just taking this Jordan form that we already know for the matrix, identifying the blocks, and then just rearranging them. However you kind of feel like it doesn't matter. There's lots of different rearrangements you could do. So what I've done here is say, well, I'm going to look at this first block with it's a 2x2 block with 3s on the diagonal. That corresponds to these first 2 basis vectors because it's in the first 2 columns. And I'm going to move that over here into kind of the middle, if you will. Right, I'm going to move it to where it corresponds to the second and third columns. So those 2 vectors become the second and third basis vectors of my new basis. And then proceeding, we're going to look at this. Got a little 1x1 block that is corresponds to the third column and therefore the third basis vector. And we're going to put that arbitrarily up there. First column, first basis vector then for the new basis. Whoops. And what was that? Okay, and then lastly, we're going to look at, let's see here, the last block. There's only 1 block left. That block, 4th column, corresponds to the 4th basis vector, and I'm just going to leave that 4th. So 4th. Okay, so there's our new basis. Again, all I've done here is rearrange the blocks and correspondingly then reorder the groups of basis vectors to get a reordered basis. Okay, so instead of green, blue, orange, we're doing blue, green, orange. Okay. All right. So that's a new basis. This matrix here represents with respect to that basis. Right now, of course, we know from previously, I mean, this up here, this matrix there, J represents with respect to the V basis. So, so what's the relationship between that matrix with respect to the new W basis and this matrix with respect to the new script V basis? Well, same linear transformation. It's now we're just changing from the V basis to the W basis. And the way we do that, of course, is with a change of basis conjugation. Okay, so it's just kind of a different take on ideas we've already talked about. Now, having written that down, you can see we do have this matrix now. We have this new matrix, J2, and I do have it written as a conjugation. But the question specifically was find the change of basis matrix C. All right, so the question specifically was to find the matrix on the left in the conjugation, because again, that's how it was written here. The one on the left. Arbitrarily how the question was, what the question's asking for, whatever. But now that we realize, okay, I want the one on the left, here it is. one on the left. And we have a simple process for how to figure out what that matrix is. This is just a change of basis matrix. So I need to look at these vectors and figure out how to write them as linear combinations of those basis vectors. So said differently, I need to take these vectors and write them in that language. And so we're going to do that one at a time. First of all, let me remind you real quick, flashback, what is this script V basis? Here it is. And I'm not going to scroll back up here for each one, but I'll just observe the script V basis is V1, V2, V3, V4. So they go in kind of numerical order. So let's keep track of that. And as we do down here, we will notice, so first column, I need to take the first one of these vectors. That is V1. And V1 is a combination of these vectors. How? Right? What linear combination of these script W vectors, what linear combination of those gives me V1? Well, 0 of those, 1, oh, there it is, see, 1 of those. And then 0 of those and 0 of those. So V1 thus telling me the first column, its coefficients in W language are those numbers. Likewise, V2, there it is. So I'm going to get 0, 0, 1, 0. And then likewise, V3, oh, there it is. So V3 is this linear combination of those vectors. And V4, there it is. V4 is this linear combination of those vectors. And there's my change of basis matrix, right? So ultimately kind of a straightforward process here. And let's see here, I zoom out. Realizing that the way to understand what this matrix C is to realize how it is a change of basis matrix relating to the basis, that's the language for that matrix, and the basis, that's the language for that matrix. And once you have those bases identified, once you see how you're going to reorder the blocks, you see therefore how the bases are reordered, then that tells you how to view these as a combination of those and thus giving you your columns. Okay, so again, a little bit different from other questions of this same on this same topic, but ultimately all the same ideas, just kind of in a different order and with a different veneer. Okay, so I hope that's a useful discussion.